So in this video, we'll talk about another test that we can use to determine whether a series is convergent or divergent. It's called the integral test. And you're probably thinking, oh no, do we have to do integrals again? I thought we were done with that. Yes, sorry. You'll see integrals in this video, and you'll see integrals in, a few other videos in this chapter. But we'll see how this test can be used, right? We'll see how integrals can be used to determine that certain series converge or diverge. And I'll start with an example that we've seen before. It's the harmonic series summation n equals 1 to infinity of 1 over n. Right? So again, this is 1 plus 1/2 plus 1/3. The sum of the reciprocals of all whole numbers. Right? 1, 2, 3, 4, and so on. And we already mentioned that the test for divergence does not apply. The limit of the individual terms is 0, right? As n goes to infinity, 1 over n goes to 0. So we can't really use the test for divergence. It doesn't tell us anything. So what now? What do we do in this case? So I'm going to do something here where I'm going to draw a pair of axes, all right? And then say, what if we consider the function f of x equals 1 over x? And maybe looking at the function can tell us something about the series. We've seen that it works for sequences, right? How about for series? Okay, let's draw the graph. I'm not going to draw this to scale here. Let's see. Maybe this is 1 in the y-axis. This is 1 in the x. That's 1/2. That's 1/3. That's 1 over 4. All right, and it's going to go to 0. Can we represent this series as an area here on this axis? I mean, when was the last time you saw the summation symbol? It was for Riemann sums, right? Riemann sums for our definite integral, remember, they represent sums of areas of rectangles that we can use to approximate the area under the curve of f of x. So what does this sum represent here? Well, it goes to infinity, right? But let's not think about that for now. 1 over 1 plus 1 over 2 plus 1 over 3 and so on. Well, 1 over 1 is the area of this rectangle here, right? Its width is 1, and its height is the y coordinate when x equals 1. So that's 1 over 1, right? It's the function value at x equals 1. How about 1/2? So 1/2 is the area of this rectangle. Again, it has width 1, and the height, we're using the what? The left endpoint here, right? And the left endpoint is f of 2, which is 1/2. And we can continue. The area of this rectangle is 1 over 3. The area of this rectangle is 1 over 4, and so on. So as a sum of areas, this series here actually represents the sum, or I'm just going to say the total area of these rectangles. And there are infinitely many of them, right? these are just the 4 rectangles corresponding to the first 4 terms of my sum, but the sum goes on forever. So I'm basically adding up all these areas forever using the left endpoint rule. Okay, that's all well and good, but what does that help us? Well, we know from previous discussions that the improper integral of 1 over x dx from 1 to infinity is a divergent integral. That's, again, you should remember how to do this, right? You just cut off the integral, make it from 1 to t, take the limit as t goes to infinity, and you get ln of t as t goes to infinity, which is infinity. Okay, so that integral diverges. But that integral really represents the area under the curve from 1 to infinity of this function f of x. Right, so it's this part, this area below the curve here. What does that tell us? Well, it's a decreasing function throughout, and you're using left endpoints. So your left endpoint approximation, well, that's going to be an overestimate, right? For this example, we're just going to say, well, the total area here is larger than whatever this improper integral is. But this improper integral, now again, we know it diverges. Therefore, it doesn't have a finite value. Because of the direction of this inequality, that means the total area of these rectangles, it's also not going to be a finite value, right? Because otherwise, if the series were convergent, then this improper integral would be convergent as well, because it represents an area that's smaller than the total area of all the rectangles, right? Therefore, this series is a divergent series. Okay, so that was nice. We see integrals again. In fact, we see improper integrals, and this improper integral told us something about the series. Can we use the same technique in order to conclude that a series converges? Well, the answer is yes. Let's change the series to 1 over n squared and see what happens there. I'm going to draw the same pair of axes. And graph of 1 over x squared, right? So that's my f of x in this case. And I'm not drawing this to scale, right? So whatever, if that's 1, I'm just going to mark whatever y coordinate is correct here. So that's 2. So clearly that's not 1 over 4, right? But it's not drawn to scale, so just ignore it looks like a line from 1 to 3, but whatever. 1 over 9. It's just to visualize what's happening here. Draw it on Desmos or something if you want. Okay, so we already know, again, that the improper integral of 1 over x squared dx converges. Okay, and in fact, we know exactly what the value of this improper integral here, right? It's equal to 1. Again, if you do that technique, solving improper integrals. So since we want to conclude that it's convergent here, we should find a way to represent this series again as a total area for infinitely many rectangles, but in the reverse inequality direction. Somehow we want to show that this series is less than the improper integral. Because we already know that the improper integral converges. So if we are able to express this series as basically a series of rectangles under the curve, then we have what we need. Okay, so I'm going to do that. Instead, I'm going to take the right endpoint. Okay, I'm using blue for my rectangles. Use blue here. That's the first rectangle. All right, so that's 1 over 1 squared. This rectangle is 1 over 2 squared. Since I'm using right endpoints, 1 over 3 squared, and so on. All right, and so all my rectangles here, that's going to add up to whatever that infinite series is. Although, note that if I wanted to compare it with the area under the curve from 1 to infinity, that actually means that I should ignore the first rectangle for now, right? Because I'm starting my improper integral at 1. Right? So this improper integral is equal to this area. Everything under the curve. So in fact, the relationship I get here is that this infinite series starting at 2 is less than the improper integral, right? Because this is represented by the sum of these rectangles, except for the first one. But that's fine, right? I can just add 1 to both sides here. And I know the improper integral is actually equal to 1, so I get the inequality. This infinite sum is less than 2. And that tells me it's convergent. Right? I mean, I know the terms are all positive here. And it doesn't contradict the test for divergence or anything. 1 over n squared, it goes to 0. And this tells us that whatever sum it approaches, it's going to be less than 2. Okay, so that's nice. We're able to use integrals in slightly different ways. 1 over n is divergent. 1 over n squared is convergent. Now, it turns out that using the same technique, you don't actually have to draw the Riemann sum each time and look at whether it's an overestimate or an underestimate or whatever. The integral test will conclude that a series converges or diverges simply based on the convergence of the improper integral. Now you have to be careful here. This only applies if f is a continuous function, a positive function, and a decreasing function from 1 to infinity. But as long as your function f satisfies all those things, and a sub n is defined to match the function values at all the positive integers, then knowing whether the integral converges or diverges is enough to tell you whether the series converges or diverges. Now, a few notes here. It's not actually necessary that we start the sequence at 1. I could also start the sequence at like 10 or something. And looking at the same improper integral will give you the same result. And simply the reason for that is saying that a series converges or diverges is really saying something about the long-term behavior of your series, right? What happens if you keep adding terms as n goes to infinity. So in a sense, it doesn't matter where you start. I could have started at the millionth term, for instance. And the same analysis will also tell you whether it's convergent or divergent. You don't even have to start your improper integral at 1 by the same reasoning. I can use the improper integral starting from 100. And by that reasoning, your function doesn't even have to be like decreasing, for instance, throughout the whole interval from 1 to infinity. So as long as your function is, it could be like that, but as long as it's eventually decreasing, then you can use the integral test. And finally, one last thing to note here is that if the series and the improper integral are convergent, they're not going to be equal generally. And we saw that on the previous example for 1 over n squared. Now, you can try this yourself, and this is actually done in your textbook, but you can characterize the values of p for which this series converges. 1 over n raised to p. We already saw that for p equals 1, you get the harmonic series and it diverges. Right? So that's 1 over n to the first power. 1 over n squared, it converges. In fact, by the test for divergence, if p is not positive, it's also going to diverge. Right? For instance, if you have like 1 over n to the minus 3, then that's just n cubed, which goes to infinity. Right? So for these values of p, it diverges. So try this yourself. It's an easy exercise. I'm going to be comparing it to the convergence properties of this improper integral. And again, before you use the integral test, you have to argue that whatever function that is you're using satisfies 3 things, right? Continuous, positive, and decreasing. Right? So try that yourselves.